last time. Kill my video. All right, so this is going to be the last one of these, or at least the last one that I have planned. If there's interest in more, we could potentially talk about that, but I probably want to take a break for a little while. So the thing that we're going to finish up with is how we can actually calculate the structure factor, or this quadratic coefficient of this free energy expansion that we talked about last time. And so we're going to bring together a couple of the ideas from the last two lectures. The one on Monday where we developed this weak inhomogeneity expression, where we could write the densities and the partition functions as a Taylor series expansion in the fields, and that let us introduce the Debye functions. And then last time we saw how we can use the density functional theory framework to come up with an expansion for the free energy of the system as a power series in the density. And today we're going to bring those two things together so that we can get the kind of weak inhomogeneity form of the free energy as a power series in the density. And we're only going to do it up to quadratic in order, but of course you can take this up to higher order if you have the patience to grind through the algebra. But as you'll see, the algebra, even at quadratic order, is not insignificant. All right, so let's get started. So the thing that we have to remind ourselves of is the model that we're working with. So we're going to be continuing to work with what's called Model A in Glenn Fredrickson's book, or the Edwards model, and we're going to assume that we're thinking about this model in the presence of one of these external biasing fields that we introduced last time. And if we just jump straight to the field theoretic version of this model, then we expect it to be something of this form. And we wrote this down last time, that this guy was 2u0 squared, and minus n log q, and then I used a shorthand mu for the overall potential, and then mu is of course a spatially varying beast, and its mu of r is I w of r in general plus j of r, right? So this is the extra field that we're tacking on. And then when we do the weak inhomogeneity expansion, we're going to write this as I times w star, so that whatever the mean field configuration is of w of r plus some perturbations around it, and then plus j of r. And of course, last time, from the way that we define these things, both the integral of epsilon of r and j of r both integrate to 0. And then we also wrote down last time that we have the mean field equation. So if we have at mean field, we have that dh dw equals 0, and that's equal to, we have w of r over u0, and then plus I density operator rho of r. And so we can get the expression for w star just so that we have the kind of homogeneous mean field result, just by assuming that j equals 0. So if j equals 0, then we get that w star, and we can just basically solve this equation for w star, assuming that everything is homogeneous. And this is minus I u0 in n over v. Easy enough. And then to treat the case where j star is not 0, so when we have this external biasing field that's imposing some kind of density, that's imposing some density variations on the system, what we're going to do is use the mean field equation that we have up here. So we're going to use this guy, and then we're going to evaluate it using the weak inhomogeneity expansion with the external biasing field in place. All right, so for j of r, we're going to use not equal 0, sorry. We're going to use the mean field equation plus the weak inhomogeneity expansion for the density. Right, and so what we get So first, let's write down what this density operator is going to be. And so from the weak inhomogeneity expansion, we saw that this should be n over v, 1 minus n, and then a convolution dr prime g d r minus r prime. And then for the spatially varying part, we have I epsilon of r plus j of r. And close that bracket. I think I got everything. And because we're dealing with this convolution, it's going to show up, actually, let me see. This should be of r prime. Sorry about that. And since we have this convolution, it's going to be convenient for us to get rid of the convolution so that we can just deal with everything algebraically. And so most of what we're going to do today is going to be done in Fourier space. So in Fourier space, so if we Fourier transform this guy, we get rho hat of k. This thing is going to be n over v, so the constant's still there. The 1 just simply becomes a delta function, so this is delta of k. And then this just becomes a product in Fourier space. So we just have minus n gd hat k times I epsilon hat of k plus j hat of k. All right. So now we go back to our mean field equation. So we have, let me see. So we go back up here, and now we can start plugging some things in a bit. So we have, so the mean field equation. W of r over u0 plus I rho tilde of r equals 0. Right, that's the equation that we wrote down above. We plug in our expression for W of r, so we know that this is going to be W star plus epsilon of r over u0. And then for rho tilde, we have plus I. Oh, sorry, let me see, put this out front, n over v, 1 minus the convolution of this thing. Then this will be I epsilon of r prime plus j of r prime. And of course, all this is still equal to 0. We can plug in for W star. So we have that up here if we scroll up. So W star was minus I u naught n over v. And we can start simplifying some things. So this is going to be equal to minus I u naught little n big N over v over u naught. So I'm going to break this term up into 2 parts. Then we'll have plus epsilon of r over u naught. And then we also have, this hot mess over here. So we can go ahead and distribute this guy. We have plus I n over v. Then minus, let me see, I'm missing. Yep, sorry about that. I missed a factor of n here. So make sure to catch that guy. So this is minus I little n big N squared over v. Integral dr prime gd r minus r prime. All right, now we can simplify a little bit here. So one thing that's going to go away, obviously these u naughts are going to cancel. So then that gives us minus I little n big N over v. And so that will cancel, that whole thing is going to end up canceling with that guy. So those terms are gone. And then we'll flip back to Fourier space so that we can write this a little bit more compactly. So again, we'll go to Fourier space. And we'll have epsilon hat of k over u naught minus I n squared over v gd hat of k I epsilon hat of k plus j hat of k. And all this still equal to 0. Right, and so now the thing that we can do here, and well, let's finish the algebra and then I'll talk about it for a moment. But we can solve for this epsilon hat, this field that comes about through the interactions, and express that in terms of this fictitious external field that we're imposing, j hat. Right, so we can rearrange this thing so that we can just straight up solve for epsilon in terms of j. And so, all we have to do is just simply multiply these things out. I'm going to start introducing, I'm going to start using the rho naught variable. So we'll use that guy when we come down to the next line. And I'm going to multiply through by u0. So we will have epsilon hat of k minus I rho naught u naught n. Then divide function of k. We have another factor of I here, so I'm going to separate the sum into two terms. We have another factor of I here, so that's going to kill off the imaginary unit and make this a plus, so we can do that. So the I is gone, and we have rho naught u naught n hat epsilon hat of k, and then we'll have minus I rho naught u naught, all the same stuff multiplied by j. All right, and now it's straightforward to just factor out the epsilon on the left-hand side, and we get a clean expression relating the two fields. And so we can express the equilibrium field in this manner. So it's I u naught rho naught n of k over 1 plus u naught rho naught n gd hat of k, and then all times j hat of k. And so I have to admit that I find this step to be a little bit perplexing. On the physical intuition that goes into this, developing this relationship, it's a little fuzzy to me. I think the way to think about it is that what we're doing is that we're imposing this external field j, right, to prescribe some density rho of r. And then my interpretation of this is that we're then solving for the equilibrium field that we would need to get the same density, right? Or we're solving for the relationship between the equilibrium field that would give us the same density as the one that we're imposing through j. But if others have different interpretations of that, I'd certainly be interested in hearing them. But anyway, it's yeah, the physical content of this equation is always a little bit opaque to me. But regardless, we can take this result that we have and we can plug it into our Hamiltonian and into the partition function and derive the Helmholtz potential as a functional of j now, right? We can get the equilibrium field out of the equation altogether, and we can write that Hamiltonian as a functional of j, right? So now we can take this thing and plug into our h and q to derive a of j. And the algebra through this gets a little bit hairy, but I like to show the work just simply because it seems like it comes out of nowhere if you don't. So, bear with me as we go through this. All right, so first, let's write down our Hamiltonian. We have 1 over 2, 0 integral dr. And then we have, so this is where the field W of R all squared goes. And so we have W star, which we've written above was minus I u naught rho naught, right? And then plus epsilon of R squared, right? So that's our W of R squared, then minus n log Q. And of course, with Q, we're going to end up using the weak inhomogeneity expansion version of it. And so we're going to end up with some rather cumbersome equations to simplify. But first, we can deal with this guy because it simplifies quite readily. So let's deal with this thing first. So if we have, let's see how I want to write this, make sure I get this right. So we have this first term is just 1 over 2 u naught integral dr. And then we can multiply out this quadratic. So we'll have the minus signs multiply each other together. So the minus signs go away, but then we have I squared. So we pick up another minus sign. So that's going to be minus u0 squared rho 0 squared. Then we have plus 2, right? So from the square, we have 2I u0 rho 0 epsilon of r. I guess that should be a minus, right? And then plus epsilon of r squared. All right, so this first term is just a constant, so it doesn't give us anything. We can just pull that through the integral. We take the integral of the first term and we just get a volume. So we'll have minus u0 rho 0 both squared over 2 u0. Obviously, that guy's going to cancel. And then the integral gives us a volume. This next term is a bunch of constants and then multiplied by the integral over space of epsilon. So that also gives us, that's going to give us a 0, right? Because we defined epsilon to be the deviations around the average field, right? So then we're going to have minus 0. And then the only thing that really survives of any significance is the epsilon squared term. Right? So this is plus 1 over 2 u naught integral dr epsilon of r all squared. And eventually, in the end, we're going to want everything in Fourier space. And so we know that we can write one of the Fourier transform properties that we've been exploiting a lot is that we can write this as, so we still have our constants rho naught squared, v over 2, then plus 1 over 2 u naught. And then we can write this integral of a function times another function as epsilon hat of k, epsilon hat of minus k. All right, so that's all we need for this guy. Now we do the same. Now we do the same bit of simplifications for minus n log q. So if you recall, what we had before, or what we derived a couple of lectures ago, was when we had a field that was IW, I'm sorry, it was just W. It was just W of R. My apologies. We showed that this thing could be written as e to the minus W star of n, and then 1 plus n squared 2v squared sum over k, epsilon hat of k, epsilon hat of minus k, and then Debye function. Right? And when we did this whole derivation, the field that we started with in the equation was W of R was equal to just W star plus epsilon. And when we work with the actual model A, right, when we do derive the field theory, the change that we have to make is that instead of we have this imaginary unit that multiplies the W of R everywhere. So we have to incorporate that in. And we're also adding in this this field J of K, right? So everywhere what we have to do is go into our equations. We need to take W star is going to go to I times W star, right, to reflect the form of the field that we're working with. And epsilon of R is going to go to, actually, we're going to do this in Fourier space. Let's go ahead and just write it as epsilon of K. This is going to become I epsilon hat of K plus J hat of K. Right, just because of the different starting point that we have in this derivation compared to when we originally derived this expression for the homopolymer. All right, so when we do that, obviously the equations are going to get a little bit more horrific. So we plug that in and we get e to the minus I W star n. Then we'll have 1 plus n squared over 2v squared sum over k. And then again, where we have this epsilon hat of k, we're going to replace it with this. And so I epsilon hat of k plus j hat of k I epsilon hat of minus k plus j hat of minus k. And then we still have our Debye function. And we have to close our brace. All right, well, so now we have this lovely little monstrosity of an equation. And the term that we actually need to evaluate to get the equation for the Hamiltonian, though, is minus n log q. So now we have to multiply all of this stuff by minus n and take the natural log of this whole thing. And so, of course, we have an exponential times a whole bunch of stuff. And so the natural thing to do is going to be to make that a sum of two terms. So when we have the log of the first term, that's just going to, it's a log of an exponential. So obviously it's going to give us a constant. So if we have minus n log q, this is going to give us minus n, and then the log cancels out with the exponential. So then we have minus I w star n, right? That comes from the first exponential, and then minus n log of 1 plus n squared to v squared, sum over k, and then all of this stuff, right? So I'm just going to use carets to indicate that it's the stuff above, but it's, that term, and the Debye function, just so that we don't have to write it all out again. And everything that we've been doing has been under the assumption that all of the field variations are relatively small or they're weak. And so what we're going to do is now assume that this whole term is also small, right? Because it only depends on the fields, and it's all the fields multiplied together. And so we're going to, exploit the fact that that's assumed to be a small number. And so then two things that we're going to do when we go to the next line is that we're going to plug in for W star. So this is minus I U naught rho naught. And then we're going to use the fact that log of 1 plus x is roughly equal to x if x is small, right? So we use that Taylor series expansion. And so then we get that minus n log q, right? This term becomes, let me see. So we have a little n, a big N. Oh man, we have so many minus signs floating around. So we have 1, 2, 3 minus signs, and then I squared. So that's a fourth minus sign. So the whole thing ends up being positive. Then U0, rho 0. And I'm also going to take, well, I'll come back to that point. And then again, we have this term that's going to survive. So we'll have minus n, this whole term. That's going to take the form. So I'm also going to collect the rho naught. So when we do this expansion, we're going to end up with little n times n squared over v squared. And I'm going to take out one of those big N's and one of the V's so that we can insert a rho naught. So rho naught n over 2v. Make sure that agrees with my notes. I think it does. Yeah, and then we have sum over k, I epsilon hat of k plus j hat of k. Same thing at minus k. And then Debye function. All right, now we're getting there. So the next thing we can do to simplify this, and then we'll plug everything back into H. So we're going to take this term and we're going to multiply and divide by the volume. And that'll let us get a rho naught squared here in the first term. And then, all right, so now we're just going to do that and then just go ahead and plug back into H, right? So that we can start combining things. right, so when we do that, so let me scroll up and look at my equation. So in the equation that we had above, we have this minus u naught rho squared v over 2. And then here, when we introduce multiply and divide by this v, that's going to give us a plus u naught rho squared, and then v. Right, so we have the same term, it's just that it's minus and multiplied by a half up above. And so we end up with just a net 1/2 rho naught squared u0 from those two terms. And then we also still have the term that depends on the wave vectors, right? So, from h, right? So we have this guy, that's still around. So we still have to carry around that thing, right? So 2 u naught v sum over k. Where did it go? Epsilon hat of k. And then we have the term that we just derived, this guy, this whole mess here that I think I'm just going to cheat and copy it and paste it in place. All right. Okay, so again, we have a big old hot mess of an equation. And now the thing that we have to use, and this is where it gets briefly really, really painful, is we have to use this relationship that we derive between the equilibrium field epsilon and the imposed field J. We're going to plug that into this monstrosity and then simplify it. And it does actually simplify quite a lot, but as you can imagine, it's non-trivial to get there. All right, so let's see how we're going to do this. The first thing we're just going to break this guy up into 3 terms, and then we're going to attack them one at a time. Oh, I did not mean to do that. Sorry. Thank you. So this guy, we're just going to call our constant. This is h0. And if you look at this, you can hopefully interpret this as just being a simple mean field estimate of the energy, right? It's the square in the density, the magnitude of the characteristic energy scale of the interaction, and it's just 1/2 density squared energy scale, and that gives you a mean field estimate of the energy of the system. This term, I'm just going to call it term 2, and this one will be term 3. I may not show every single grueling step of this because it does get kind of horrific, but we can at least highlight the key details. So now this is where we're going to plug in our epsilon hat of k. This is I u naught rho naught and the Debye function of k all over 1 plus u naught rho naught and the Debye function of k. Oh, right, of course, times j hat of k. So when we do this in the first term, or in term 2, so term 2, this one's not so bad. So the prefactor stays the same. We have sum over k. I can do better than that with my sigmas. Sum over k. And then I'm going to so we have epsilon of k and epsilon of minus k. And so that's going to give us a j hat of k and j hat of minus k off to the right. And I'll remind you that the Debye function only depends on squares k squared everywhere. So it's an even function. So g hat of k is equal to g hat of minus k. So we don't have to care about the sign of the k there. And so I'm going to take this prefactor and multiply those two things together. So we'll have keep things in the right order, u naught rho naught n g hat d of k all over 1 plus u naught rho naught n g hat d of k. And again, because the Debye function is an even function, we can just square this thing as opposed to having to multiply it by the minus k thing. But we don't have that kind of information about j hat, so we have to have j hat of k and minus k. All right, so then this term just simply becomes 1 over 2 u0 v sum over k, and the i's give us a minus sign, and then we just have kind of the usual form: rho naught squared, n squared, divi squared of k, and then the whole denominator squared. 1 plus u naught rho naught n all squared. Then j hat of k, j hat of minus k. All right, and for now, that's all we can do with this guy. Now we go up to term 3, and this is again the kind of painful one. So let me see, how did I? So, all right. So now when we plug in this this epsilon hat, this thing in here, we're going to have some messy factor that's a function of k multiplying j hat of k, and then plus j hat of k right afterwards. So we can factor out that j hat and just put it off to the side. And the same thing is going to happen over here, right? Where we have something times j hat of minus k, this whole thing times j hat of minus k, then plus j hat of minus k. And so we can just, isolate the j hat terms by themselves. And then as the prefactor, we have minus rho naught n over 2v, sum over k, and maybe we'll just put the j hat of k, j hat of minus k out front. And we have I times epsilon hat and I of k, and then now this is going to be plus 1. So we have this, right? So we have I, and then the actual epsilon hat is I u naught rho naught n gd hat of k all over 1 plus u naught rho naught n gd hat of k. Right, so that's from plugging in for epsilon hat, and the j hat we've already taken out. And so then we just have plus 1. And then now we have the same thing from the minus k term. Right, so then we have I u naught rho naught n and plus 1. All right, I think that's right. I seem to be missing. Yeah, I missed this guy. So let me make sure that I get that thing out here. So we should have in here multiply by the divi function, g hat of k. So I missed the divi function, so make sure that you catch that guy, or you can throw it off to the right if you have room on your page. Okay, and so this is where the algebra kind of stinks for a minute, because what we have to do is multiply these two things out. Well, I guess first of all, we can get rid of the imaginary units easily enough, right? So that just gives us a negative sign, that gives us a negative sign, no sweat. But now the kind of terrible thing that we have to do is multiply these things out. And so that's going to give us 3 terms, because we're basically, have something squared. And then we have to go through the hassle of creating a common denominator between the 3 terms, because if you kind of envision this, the first term that we're going to have is going to have this denominator all squared in it. And then we'll have a plus another term that's twice this thing with only this linear in the denominator. And then we have plus the constant 1. And so in each of those, we have to find a common denominator by multiplying and dividing by the appropriate power of this bottom term. So that's kind of what makes the algebra a bit horrible. So, but it's relatively straightforward stuff. It's just easy to make mistakes. So hopefully I can get through this without messing it up too bad. All right, so the first term, we have 2 minus signs. So that's the minus signs will cancel. Then otherwise we'll have u naught squared, rho naught squared, n squared, gd hat squared, 1 plus u naught rho naught n gd hat. Then all of that squared. All right, so that's our first term. then minus 2 because we're squaring the things, u naught rho naught n gd hat of k 1 plus u naught rho naught n gd hat of k, then just plus 1, right? Yeah, then plus 1, close our brace, and we have divide function j hat of k, j hat of minus k. Ugh. All right, and now I'm just going to skip the algebra here so that we don't have to actually grind through it all because it is rather grueling. And a ton of things end up canceling out. So the simplification actually ends up being kind of miraculous. So the steps here to find a common denominator. And then you cancel terms. And what you end up with is minus rho naught n over 2v sum over k. Get a lonely divide function in the numerator. And that's the one that's from out at the right. So basically a 1, after you collect all the common denominator here, a 1 is the only thing that survives. Then you have 1 plus u naught rho naught n gd hat of k squared, and then j hat of k, j hat of minus k. And again, it's straightforward to work through that algebra. It's just a little bit tedious. And then the kind of common form that this is usually written in, or the way that we're going to want to write this so that we can combine it with the thing that we have from term 2 above, is we're going to multiply and divide this thing by a factor of u0. Right? So we're going to insert a u0 here and a u0 here, just a constant. And then this is all just going to be minus 1 over 2 u0v sum over k rho 0 in u0 divide function 1 plus u0 rho 0 n divide function of k. And then j hat of k, j hat of minus k. All right, we are getting somewhere. So let's scroll back up and see what we left our term 2 as. So the denominator we can see here is common between the two. See, did I miss? Hold on. Oh, right. Okay. So yeah, when we go back up and add this to this term 2, what we see is that the denominator is common between the two. And so we can add what's in the numerator together, right? So we can take, right, because let me see, this should be squared. Sorry, I forgot that squared. So we have the same prefactor, the minus 1 over 2 u naught v, and then all of this mess squared. So that gives us the same prefactors up here. So 1 over 2v, hot mess squared. And then we have the same thing multiplying on the right. And so the only thing that we get in the numerator is going to be the sum of the two numerators. All right. And so the one from above is minus u naught squared, rho naught squared, n squared divide function. And then here we just have rho naught, u naught, and divide function. So when we take term 2 plus 3, what we have is minus 1 over 2 u0v sum over k. And then again, I'm going to zoom out a bit so that we can see the two terms. The things that we're adding together is this plus this, right? And you can see that in both of them, since we're adding them together, we can factor out a rho naught n u naught gd divide function so that we have just 1 minus the same factor. Actually, no, I'm sorry. 1 plus the same factor because both of them are carrying a minus sign, right? So we have rho naught u naught n divide function of k times 1 plus rho naught u naught n divide function of k, then over 1 plus u naught rho naught n by function of k all squared, and then j hat of k, j hat of minus k. All right, we are almost there. And so, of course, the reason why we factor this thing out is so that we can cancel that guy with the square and get the final simplified form. So finally, for the Hamiltonian, what we get after all of this mess, we get that h is h0, so that constant mean field term, and then we have an added correction due to the spatial variations that we're allowing. All right, so we have 2 u naught v sum over k rho naught n by function hat of k 1 plus u naught rho naught n g hat of k, and then j hat of k, j hat of minus k. And if you happen to have Glenn's book, this is the final result of equation 5.24 in the equilibrium theory of inhomogeneous polymers. So that's how you derive that equation. And now the thing that we can do is start, now really what we have is, to within a constant, this is also equal to our functional, the Helmholtz free energy as a functional of this imposed field. And if you recall, what we knew from the density functional theory that we derived last time is that if we take the variation of this with respect to J, then that gives us the average density. Right, so now we can look at del H del J of R. Right, this gives us the average of rho. Let me see, I have to talk about a detail here. Well, so we know this to be true. And from the initial discussion of the calculus of variations, what the way that we talked about taking functional derivatives is that we're basically imagining going to every single continuous point along the function and allowing it to vary over all space. And the thing that I'm going to argue is that you can also do the exact same thing in Fourier space, right? Because representing a function as a Fourier transform is kind of an equivalent representation. And so you can also go to all the Fourier amplitudes and vary those over all the possible allowed values. And so we can also say that this equation will also work in Fourier space. So if we do dh d j hat of k, this will give us and again, I'm going to kind of cop out and go into the notation that Glenn uses in his textbook, where this is called delta rho hat of k. Because the mean field, all the mean field contributions are buried in H naught, this variation that we're calculating is only going to give us the deviations around the mean field value, right? It's not going to give us we would have to add the mean field value onto the final solution that we get. But regardless, with the equation that we have up here, this is an easy derivative to take. This variational derivative is just going to kill off the sum over k and kill off one of the j of k's. Let me see what else. We should have another simplification that we can make. Oh, yeah. So I missed this u naught when I copied this down. So this guy should be there, and then that kills off the one that's in the prefactor. And so what we get for our dh dj hat of k is just simply minus rho naught n g hat of k. Let me see. 1 plus u0 rho 0 n gd hat of k. And so let me see something. Yeah, so the prefactor of 1 over so the other thing that's gone here is the 1 over 2v. So the volume goes away with this sum over k when we take the variational derivative, because again, if you remember, the functional derivative is or this sum over k is what brought in that factor of 1 over volume. So that gets killed off there, and then the 2 gets killed off because we have something that's j squared, right? So this is still just j hat of k, and that's what kills off the 2. And so now we know that this is equal to our delta rho hat of k. And so now we can invert this thing, right? So now we can solve for j hat of k in terms of delta of k, and then we're basically done. So now we get that j hat of k is equal to minus 1 plus u naught rho naught n the bifunction hat of k, right? That's from the denominator, and then over rho naught n gd hat of k, then delta hat rho of k. And so then finally, the thing that we've been after all this time is going to be our density functional as a function of so the free energy cost for perturbing the density away from its average. Right? So when we write it in this delta rho, we can write that as, let me see, we can write this as, this is going to be our, remember, it should be a of rho, or a of j, then minus 1 over v, sum over k, j of k, delta rho hat of k. I'm sorry, this should be minus k. Apologies. Come on. My pen's not wanting to work all of a sudden. There, minus k. And again, this is from that definition of the Legendre transform, and this a of j is still just going to be equal to our Hamiltonian, right? So this is w of j minus 1 over v, sum over k, j hat of k, delta hat rho of k, minus k, sorry, minus k. But now basically we can just plug everything in and kind of solve it and simplify it. So this becomes just simply so again, the h of w and j, if we go back up, and we have all this stuff multiplied by j squared. So again, there's a bit of tedious algebra to simplify this thing. But because of this inverse relationship, it actually simplifies quite cleanly. So we have minus 1 over 2v sum over k, rho naught n the bifunction hat of k. All right, so this is the prefactor that we already had in the Hamiltonian, 1 plus u naught rho naught n gd hat of k. And then we had j of k times j of minus k. And now we're going to have this relationship for j of k. So we have to plug this guy in. So we're squaring it, so the minus sign is going to go away. 1 plus u naught rho naught n gd hat of k over rho naught n gd hat of k all squared. J hat of k, oh, nope, delta. This is density now. All right, so delta rho hat of k, delta rho hat of minus k. Ugh. All right, and so we have a common term here, so that is going to kill off the square there. So that's nice. And then now we still have to tack on to this the term from the actual Legendre transform. So we still have this second part that we have to add on. So we have plus 1 over v sum over k. Let me see. So we have for j of k, what we're going to have is, let me make sure that I get this right. Minus 1 plus u0 rho 0 n gd hat of k all over rho 0 n gd hat of k. right? That comes from the from j hat, and so then that's going to give us this guy times delta rho hat of minus k, and then this whole thing still has plus the mean field h0 tacked onto it. And the only thing, I mean, the thing to notice here is that after we cancel out this first term, right? So we have this, this first term is gone. We have the same, what did I mess up? Let me see. Sorry, give me just a second. I think I messed up a minus sign somewhere. Oh, yeah, there should be a minus sign in front of this whole term. Right, so this started out as minus 1 over v, just from the definition of the Legendre transform here. And then there's a minus sign in the relationship between j hat and rho. So then that becomes plus plus. And now we see, hopefully we can see that we have the same term here, except that this one has minus a half on it. Right, and so then we have, in the end, this free energy function that we get, right, because these two terms are the same, it's just there's the difference of the minus 1/2, we get f of delta rho hat. There's a mean field contribution, and then this term that comes from, that penalizes deviations around the mean. And then since we just have this something relatively simple, that we can split this up into to a sum of two fractions, and we end up with 1 over rho naught n the bifunction of k, then plus u0 delta rho hat of k delta rho hat of minus k. And then again in Glenn's book, so this is equation 5.26. So, you know, as you might imagine, since the equation number only went up by 2, the book doesn't show a whole lot of the algebra. And so this is it. So this, the way that we think about this and the way that we interpret this is that this prefactor basically gives us the structure factor that comes about in the system due to the quadratic density flux, the quadratic level density fluctuations in the system. And so this coefficient, this, which I'm just going to call this thing gamma hat of k, if you remember, this thing was related to the average of the density at r times the average of the density at r prime when we went through the density functional theory stuff, right? So this thing really is just 1 over, I'm sorry, it's the inverse of that thing. So this is really is just ends up being just 1 over the static structure factor. And so this quadratic coefficient turns out to be really important. And the thing that we can do with this, now that we have this free energy functional expansion, is that we can analyze it for the stability of our system against fluctuations, right? So if we write this thing, f of delta rho hat, we can rewrite this guy as 1 plus 2v, sum over k, gamma hat of k, delta hat of k, delta hat of minus k. You know, for any of the sort of standard field theory models, this is the form that you end up with as the final set of equations. It's just the thing that changes depending on the interactions and the types of molecules that you build in is the functional form of this coefficient. And you can see in this form, you know, it has the u naught that comes from the interactions between the material, and then this comes from the you know, the polymeric structure of the material, or of the molecules that are in the solution. And so in this particular case, we can analyze this really easily because this gamma hat, if we were to plot the Debye function, what we would see is that gamma hat is a monotonic function of k. And so, so since we never actually sketched or talked too much about the functional form of this thing, but gd hat of k, the Debye function, is monotonically decreasing. And so what we can see is that the system will go unstable when the system becomes unstable And by unstable, I mean thermodynamically unstable. So in other words, the second derivative of the free energy becomes negative um, when gamma hat of k, um, and because of the functional form of this thing, we can just focus on the k equals 0 mode, or in other words, the average behavior of the system when this is less than 0. And so if we look at f of rho, if gamma is a positive number, we get something like this. And then as gamma decreases, eventually what we find is that it rolls over. And so this is plotted against rho. And so then this would be gamma hat less than 0. And so, of course, the critical value for stability of the system is, or the kind of critical value where the system first goes unstable. And so when gamma equals 0, then that's where we have 1 over rho naught n. The Debye function at k equals 0 is just 1, right? So g hat d of 0 plus u naught equals 0. And so this thing is equal to 1 at k equals 0. And so stability is going to, this equation is going to be true at the phase boundary. Or in other words, when the system is just right on the threshold of stability, at the phase boundary. And so then the system will be stable only when this energy parameter is greater than -1 over rho naught times n. Right, and so, and this is kind of surprising because the model that we derived this on all assumes that u naught has to be a positive number just for the math to work. But here we see that the system can actually be stable for a weakly negative u naught. And that's kind of one of the surprising results. But this also agrees very well with the kind of mean field analysis of the Edwards model. The other thing that we can discuss a little bit here is that the thing that kind of qualitatively changes when you repeat all of this mess for a die block is that the functional form of this gamma changes, right? So for a die block, right, so this gamma hat of k, right? So here the minimum of gamma was actually when we had was actually at k equals 0, right? So that was the particular mode that we needed to analyze. But for a die block copolymer, what you find is that gamma hat is not non-monotonic in k, right? And what you end up finding is that the system actually goes unstable at a finite value of k, right? And the system goes unstable for finite k. Right, so in other words, you can solve this equation up here with at a finite value of k, and of course the Debye functions that show up there are much more complicated because it's the Debye function or from the weak inhomogeneity expansion of a die block. But this is the this finite mode. The fact that this is going unstable at a finite wave vector tells you that it's the system is not going to macrophase separate. It's going to microphase separate, and so it's going to microphase separate on domains that have a characteristic size of 1 over this k. Right, and so what this means is that you get microphase separation on length scales. Of course, they're on molecular length scales, but we usually use d for this length scale, so d is roughly 2 pi over k star. So we'll call k star whatever the value is where this thing is going unstable. And so that's kind of the utility and the power of doing this this expansion. There are more things that you can do with this. I mean, for one thing, you can carry these things out to higher orders if you wish to torture yourself through all that algebra. At that point, most people would typically turn to numerical solutions to to come up with models for the system. Um, and of course, you can also come up with more sophisticated models. I mean, this has been a really powerful tool for in a number of studies where people have been interested in charge systems, because mean field analysis really doesn't give you much of anything. But for systems that involve charges, incorporating, allowing for weak variations in the fields lets you get some pretty nice insight into the behaviors of those systems. And the other thing I'll say is that there are other ways to derive these coefficients. I've gone through one of the ways. It's probably the way that I'm most acclimated with, but you can also derive these these things that are equivalent to the static structure factor by actually evaluating the Gaussian integrals that are at quadratic level in the field. I kind of prefer this way just because it makes it a little bit more transparent how to go to higher orders, but you can also get to basically the same place, at least to quadratic order, by just evaluating the integrals in the partition function. All right, so I think that's basically it. That's where I wanted to get to. Are there any questions or anything anybody wants to ask? I realized this was a grueling amount of algebra today, but hopefully it's not too bad. And it took me a long time to be able to actually get through it, so don't feel bad if you got lost in it. I just like having some availability out there of some of the work that's not shown in the papers or the books that cover these things. But if there aren't any questions, then I guess this will put a bow on it and we will be done. All right, I guess the lecture will be up on the website relatively shortly after Zoom is done processing this thing. And take care, everyone, and stay safe.